Thank you for joining us today. It's CSC241. The date is 4 October, Wednesday. We are conducting an item analysis of the Module 2 assessment that was due by 10 a.m. this morning. The original due date was Saturday, 11:59 p.m., and we extended it until Wednesday, 10 a.m. for people to finish up their solution and to engage their first attempt of the Module 2 assessment. There were 17 questions and 14 students of 18 students engaged the assessment before the deadline. The average time each student took was 19 minutes, even though they had 60 minutes. That's significant because if you think about it, there were probably questions where a student could have drafted a quick truth table, worked up some canonicals, figured out the logic statement, or drew a diagram. There was a lot of time. This is less than 1/3 of the 60 minutes allotted for this assessment. And I have a concern about that because when we have an open book test and the average student score is, well, let's see, let's do the math. That's a 63 for the first attempt. That shows that our difficulty level is increased, but what we want to do is give students the means to do better. And what I'm seeing is that we're just not taking the time to draw a diagram, work up a quick truth table, use the templates, check the facts, reference the study guides, yeah? So that's something that's significant and it's worth calling out. Going forward, for your first attempt, it's important for you to take the time, if it's open book, and you have study guides, and I go to the trouble to lay all those references out for you to have the screens open, and to use the time that you have so that you get a better first shot at this, right? Put another way, how many of you want to reconcile so many items? If the first time around you took 10 minutes more, and instead of reconciling 12 items, you only had to reconcile 4 items. Am I making sense here? Does everybody understand what I'm getting at here?
Very good.
Okay, I'm not trying to scold anyone. There's no, the goal here isn't to shame or gaslight anyone. I just want to have a frank conversation about the realities. As an instructor, I'm looking, it's like, dang, less than 1/3 of the time allowed. And we scored a 63 for an average on an open book assessment. It's a bit of a concern, right? All right, so let's go ahead and get into the item analysis, and I'll post the reconciliation. And going forward, I want all of you to promise me that you're going to spend more time as a class. You're going to spend more time on your first attempt so that reconciliation isn't as much of a chore. What we're finding is that some of our students aren't even correcting their errors before they attempt the assessment again. And that could be because there are so many errors. So it's kind of a related topic. It's a related issue. And if you invest on the front side, there's less you have to do on the back end. Okay? Just saying. So students that take more time on the initial attempt do better. They have less to reconcile and they score higher. And that's a fact. I'm not making that up. All right. So let's get back to the screen. What I'd like to do is run down the list of items as the challenge, with the greatest challenge. So we're going to hop down to the bottom here for multiple answer items. There's a couple of those where even though the scores were higher, those were worth more. So on the multiple answer, as far as the metrics are concerned, Students answered very differently on many of the items, even though their average success rate was a little lower. 63 is 7 points off of a 70, which is kind of what we're shooting for. On the difficulty level, we had 5 easy questions, 1 hard question, and 11 medium questions. So that's also very encouraging, is that we had a good mix of questions for our assessment for the first attempt. Let's look at the first item. The first item is a multiple choice question. It reads, the following Boolean function is provided. So there's a not that's applied on the right side of the diagram. Let's walk through this. The right side of the diagram, everything that comes out of this part of the logic, the combination logic gate. Why do I say there's a combination logic gate? There's an and here, there's an or here. The and comes first. So in the diagram, we'd have Y and Z hitting the and. The output of the and goes into the or with the X input. Does everybody follow what I'm saying? Based on the diagrams. Yes, no, maybe?
Yeah.
Okay. Are there any questions about the Boolean function before we continue? So part of the challenge when you're working on assessment items is to take the time to read that and then to parse out what it really means. I have two, it's a compound logic gate. I have an and I have an or. We know from the order of operations that the and comes before the or. So when I'm drawing that diagram, if I have X, Y, and Z, the Y and Z down here feed into the and. The X at the top runs into an or, and the output of the and runs into the or. I would suggest when you see stuff like this, it's a good practice to kind of have a pen and paper handy so that you can draw a quick diagram when you see something like this. So part of this is to use the tools we've been using. If you're given a diagram, then figure out the Boolean function and then work the truth table, right? But it says among the operators and inputs shown, which combination executes first? Well, here's why this is not the answer. This not is applied to all of the outputs. So this not occurs last. Everything inside the parentheses has to happen first. And maybe that's something we didn't take a lot of time discussing or reviewing in class, but we did say that a not can be on the end and it affects the output of everything combined, or nots can be used for a single input on the left side of the diagram. Can everybody see my pointer?
Yeah.
So let's see if I can. Can everyone see this screen?
Yes.
So when you have a not in a function that's on the outside and there are parentheses, and the not is applied at the end to everything that's going on inside the parentheses, it means the not is over here. In terms of the diagram, the not is here, right? So in our next module, we're going to take some more time to explain further. You can apply the not universally to all the output by parking that not right here on the single output, right? And that's true for combination logic gates or compound logic gates. If you have the not here, what you have is a bar B, or you have a not B, and that would be within the parentheses. So when you're looking at this equation, if you saw a bar Z or you saw a not Z inside the parentheses, you'd be dealing with a case that looks like this, where the not is applied to a single input and it's earlier in the process. So if the not is found inside the functional statement, that's what's happening. If it's found outside the statement, it means you've gone to the trouble to use parentheses for that function so that all the things that are supposed to happen before the not. Let's say that again. When you have things that happen in the parentheses, you have to take care of that first. If the not is outside that, it does not execute early in the process. It executes after everything else has been done, meaning the not is right here instead. There's a W1 and then there's a not here. Does that help with everyone? So
Yeah.
when you're looking at the operators and inputs, which combination executes first? And comes before or. Multiplication comes before addition. So that's why the Y and the Z are executed first. And then that output is fed into an OR, which has a third input, right, called X. Does everyone understand why this is the answer and this is not the answer? Yeah. Now, it says the not X. A number of students said the not X. If we had a not and the parentheses were between the X and the plus sign, that would be the case. What I'm saying is if we move this parentheses right here between the X and the plus, then the last choice would be true. Okay? However, it's different. Let's look at the next one, a multiple choice item that reads, what is going on with the last input variable in this Boolean function? Now here is a perfect example of what we were just talking about. I have a function with inputs m and n. I don't have parentheses, right? I don't have anything else going on else. I have an or here, but I have a not that's involved with the n input. That's why it's n bar. So a not is first applied to the n before it is combined with m using or. Put another way, this is what I have right here, except it's m and n. If I take this same diagram and I substitute m for A and n for B, that is exactly the scenario we're looking at here, okay? Any questions about this item? So a number of students answered this, they selected this, And what we told you is that not is applied first. If the not is applied last, that would be the case if we had a not outside parentheses like we did in the previous example, okay? The not is applied last if there's parentheses around here, parentheses around there, it says M or N, and the not is on the outside of the parentheses. But there are no parentheses. Not is applied first before anything else, then multiplication and division, then addition and subtraction. Any questions, comments? This multiple choice example, this is a logic statement, right? So one of the things we wanted you to learn in this module are the distinct behaviors and characteristics of an or, an and the not. When you look at the truth table and you look at the logic that comes out is always 0. Well, out is 0 if the A input is 0 and the B input is 0. Otherwise, every other time it's 1. What we're doing here is expressing the logic that goes with the truth table and the canonical, the reverse canonical. Well, actually the reverse canonical. For the logic gate, we call OR. So if we look at a truth table for OR, what we have is a single case where we get a 0, but otherwise every other case is 1. There's only one case where we get a 0. Every other case in the truth table is a 1. The only logic gate that does that is the OR. Does anyone have any questions about what I'm talking about with that example? Has everyone seen the truth tables for and or?
Yeah.
Have you seen the truth tables for and or? Let's see here.
Yes.
Okay. All right. So if I go to my NAND to Tetris, and I go into tools, and I go into built-in chips, and I go into the OR, I think. No, it's in the textbook. The textbook shows the OR, and then it shows a truth table for the OR. So that's the next item that posed a challenge for students was a multiple choice question that reads, a Boolean function with 3 inputs, u, v, and w, returns just 2 0 inputs, 2 0 outputs. So how many possible combinations do we have? How big is our truth table if we have 3 inputs?
That's 8.
8 rows, yeah.
8 inputs is correct. And just 2 of them are 0, which means we have 6 true inputs. So of the 8, 2 are 0 outputs. There are 6 outputs that are 1. So the 2 canonical expressions are u tick v tick w, or u v tick w tick. Which type of canonical expressions are these? Well, if we're talking about the ones that reflect 0 outputs, those are reverse canonicals. If we were listing canonical expressions that had to do with one outputs, it would be a standard canonical. So just remember that if you have a smaller number of true inputs, you want to use standard canonical. If you have a smaller number of reverse canonicals, smaller number of false outputs or zero outputs, you want to use reverse canonicals. The trick to understanding this question is to ask yourself, okay, how many total outputs do I have with three? How many possible combinations do I have with three inputs? 8. So the fact that I have 2 zero outputs means the other 6 are ones. I hope that helps. So the interface view, yeah. We mentioned in the study guide that there were 2 views of a logic gate diagram. The implementation view that shows the internals under the hood, and the interface view that doesn't show any of that, it just shows the inputs. The interface view of a logic gate provides detail of the internal composition. That is false, because the implementation view shows how the compound logic gate is implemented or constructed. Okay, so remember, implementation means construction, internal construction view. When you're seeing the internal composition, that's the construction or implementation of the compound logic gates. You get the detail inside it. If all you see is a big outline and you have the inputs and one output, that's the interface view, because it's only showing you the inputs and the outputs. When you're only seeing input and output detail, you're basically dealing with only the interface for that logic gate. Okay, how it interfaces, how it plugs in to the computer system. All right, that's just another way of expressing it. So that was in your study guide, and I think we've been through that before. Let's just take a quick moment to pull that up, because I want to make sure everybody's seeing that piece of it. If all you see are the inputs and the outputs, what you have is a diagram that shows how that digital component interfaces with the other physical components in the computer. So I'm using different language now to explain further. The implementation view shows what's going on inside there, how that is built or implemented out of internal parts. So this is the outside view, and this is the deep inside view. Implementation versus interface. Okay. I think we mentioned in, yeah, I'm sure we mentioned in class in one of the recordings that if you look at the backslash key on your keyboard, there's a symbol that looks like a tall vertical line, and that's the pipe symbol, and that represents the Boolean operator for OR. Does anyone know what symbol represents the Boolean operator for AND?
Say that again?
What symbol represents the Boolean operator for AND?
Isn't it the like, I don't know, if you press Shift and 7, isn't it that symbol? Or
This is not.
The not, yeah.
And the ampersand, it's called an ampersand.
Ampersand. Okay.
Ampersand. Yeah. The ampersand. Ampersand looks like backwards G. Does everybody know what I'm talking about?
Yeah.
That
No.
might be in the addendum. Oh, where is that? There we are. So it's a double ampersand. That's why they tend to use double pipes and double ampersands. In some assembly languages, very low level C language, that kind of thing, they'll use a single ampersand, so to avoid the confusion. Moving right along. So for the rest of these items, there were only a few students that missed these items since they were worth a quarter of a point, right? 80% of the students got these correct. What are the first output values and so on? What I'd like to do is skip down to the multiple answer, and then time permitting, we'll go ahead and cover the other ones, okay? This multi-answer question was a challenge. So instead of using a single letter variable, in this this is a Boolean function, right? So this is we could have the italicized F, and then it says input A, comma, input B. Instead of using just A and B. That's all we're doing here, okay? And here's the rest of it. Not, and then input A and input B. So it's an AND operator. And then once this is done, the not is applied to all of the outputs, right? So a programming statement includes the following detail to apply a Boolean AND with a Boolean not to two inputs. What you're looking at here is the very definition of something we call a NAND. When you have a not and an or, that's called a NOR, right? So we touched on this a bit, but it says this programming statement applies the not universally to all of the output values. That's correct, because it's on the outside of the parentheses. The truth table outputs will render a single zero when both input A and input B are both 1. So the only case where an AND produces a 1 is when both input A and input B are 1. That's the only time, a standard AND. The not flips it. So the truth table outputs will render a single 0 when both inputs are both 1. That's the difference. Remember we called out in class, hey, is a NAND the same as an OR? Does anyone remember that? Not too long ago I said, hey, if we put a not in front of an AND, does that give us the same thing as an OR? And the answer was, it does not. An OR is the truth table for the NAND and the truth table for the OR look similar because there are 3 1s and a single 0. but what triggers that single zero is different. I'm hoping that rings a bell. All right. The other thing that we would select to answer this question correctly would be that a reverse canonical expression, AB, represents the output of this Boolean function. So this is a case where whenever, okay, and I just want to be completely transparent with you. When you see multiple answer, can someone unmute your microphone so I'm sure we're still together?
Yeah.
Because my internet
We're still here.
Yes, we're still here.
Okay. So whenever you see a multiple answer item on a test or assessment, the midterm exam, it's, you know, we have a midterm exam coming up. We have assessments for the modules. Whenever there's a multiple answer, it means there's big points on the table. It's worth at least twice as much as the other questions. That's something that everyone needs to understand clearly. So multiple answer questions mean that there's more to it. They're scenario based. We don't have as many of them, but they're worth more. So where am I going with this? If you have something that's worth 3/4 of a point and you blow it because you're rushed and you're not taking the time to do the truth table and so on, it's often very helpful to just, you know, you have plenty of time, right? So, and I know some of you were saying, yeah, if you only knew my schedule, you'd know that weren't true. I get it. I completely get it. These are two input scenarios. The templates are so simple. There's only 4 sets of possible inputs and outputs, right? We have a template pre-built for you. So what am I saying? You can easily just use the templates, take the time, and then you can claim full credit for a multi-answer item. If you select choices that are incorrect, like this one, the truth table outputs will render a single one when both inputs are 0. The truth table outputs render more than a single one. The only way you'd know to answer that question is if you actually did the truth table. It is true that when you put 2 ones in there, a 0 comes out. But we're not talking about a single case. We're talking about the entire truth table. And the entire truth table renders 3 ones. Every case is a 1, except for a single case that's a 0, right? And that's a false statement. This statement is actually false. If you did the truth table, you'd look at it and go, no, that's not accurate. The programming statement applies the not differentially to the first input, A. If that were true, the not would be in here, and there would be a bracket. There would be another parentheses. This parentheses here would be moved right here instead. That's a specific case where the not is only applied to input A. So where are we going with this? If this were an or, if this were an or instead of, I mean, if this were an and instead of an or, what we're saying is that item says there's a not and it's parked right here going into the A instead of being parked out here. All right. I hope that helps. So whenever you see multiple answer, take more time with those. All right. And basically folks will do better. If you choose options that are incorrect, you lose points. So a standard canonical expression represents the output. The only way you'd know is if you took the time to do the truth table. And it's what is 3/4 of a point, right? So some multi-answer questions are worth 3/4 of a point. What is that compared to the 5-point total? That one question is worth 15% of your grade. Your assessment grade, 15% of that comes from this one question. So when you see multi-answer, going forward, take the time, okay? That's one reason why I was motivated to share with you what I did at the beginning of the class. Does anyone have any other questions about that multi-answer item? Let's go down to this multi-answer item. Most everyone got these correct. And this one was 80% of the students got this one correct. Let's look at this multi-answer. So I have a Boolean function with inputs n and o. It's an and because of the dot. And there's a not in there because of the, everybody see the bar? There's a bar above that O. So the not operator is applied to the O before the and is applied to both inputs. That is correct. The truth table outputs will render a single one when n is 1 and O is 0. I think we walked through this in class. We actually showed this and shared this in class. So this is an explicit example we covered in class. Most students selected this. The truth table outputs will render a single 0 when n is 0 and O is 1. That is a bogus answer. So there's a case where it's multi-answer. You should take the time to do the truth, draw a quick diagram, do the truth table, and then you can answer these things correctly. Okay, have to do that. All right, so let's draw a comparison. How many of you have been in math classes where you submitted and you were supposed to submit your answers and the instructor said, please show your work? Does anyone recall a math class where that was the case and the instructor said, hey, I need you to give me the answer to this equation, but I need you to show your work. Solve this equation, show your work. Does that ring a bell for anyone?
Yeah.
Okay, thank you. What you have here is the computer architecture equivalent of the same. If in math class you did the solution in your head, if you solved the equation in your head, and then you put the answer down and it was incorrect, the instructor was often in a bad place because they couldn't give you partial credit. They couldn't give you partial credit because you didn't show your work. What we have here is a case where students are not taking the time to use a 2-input truth table with 4 pre-configured inputs. I've done the work for you, okay? All you have to do is modify the top and the top of the template, right? So what am I saying? You go to the, you do this and you use the template and you go here, right? And all right, so you can take this out. That's not, actually that was used for another solution, but originally it just said input A and input B. And this column is blank. So usually that's what's going on with the template, okay? And all you got to do is substitute for each right? So do a save as. I'm gonna call this my NO truth table. Oh, but this has a bar, right? So what I have is a not O. It's another way of doing this. So now what I can do is this. Everybody see what I'm doing? So you get what I'm doing. This is the value we're using to combine with this column. And we're doing, what do we say? That's an and. So 0 and 1. What's my output here? Anyone?
Zero.
It is 0, thank you. And what is it here?
Zero.
0. And what about here?
1.
Oh, so the 1 occurs, it just occurs in a different place. See, that's where the wild card, that's where that wild card comes into play. And then I have 1 and 0. So the answer here is 0. So now I have what I need. Now I have what I need to answer this question. I think I can even copy and paste from here. Let's see if I can do this. Can I even copy and paste this into the table, right? So when I'm working up my solution, instead of output, oh, look at that, right? I can do this right here. Instead of having this, I can do that. Everybody see what I'm doing? This took a minute or two, a couple of minutes, right? But now I have exactly what I need. So when I'm answering those questions, I'm not losing credit by choosing answers that are incorrect. The other part about multi-answer questions, I want you to understand the reason you take more time with them is because if you select incorrect items, points are taken back. You lose points, right? So that's another aspect of multi-answer you want to remember. We're almost done and then we'll be ready to clear. So these answers were good. The true and false here, all but 1 or 2 students had that incorrect. Let's go back up to here. Does anyone want to see this multiple choice item? No, I think we did that one, UV and W. Primitive logic gates. True, false. The most primitive Boolean or logical components are NAND and NOR, since either can be used to create basic logical operators. That is a true statement. That's something right out of the study guide, actually. So this concludes our item analysis for the Module 2 assessment. I will post the reconciliation in Module 2, and if you could finish that up by the end of the week, that would be great. Please join us on Friday. We'll be doing some things in the hardware simulator. Bring your tech, bring your hardware simulator. We'll walk through some examples and we'll begin we'll take up the rest of our content review for Module 3 on Friday, and we'll do some hands-on on Friday. Okay? Thank you for joining us. Stay dry, stay safe. Bye-bye for now.
You do the same.